exercise show that any monotone function on a closed interval AB is Riemann integrable. Yeah, you just need to write it properly. Proof will follow. All right. So what next is what the definition you have seen in the first year will prove that is equivalent to this one. All right. So if you look at a partition and tag it up by any points in that in each of the subinterval and look at the functions evaluated on that tag points times the length of the subinterval and sum it up. So that will give actually, if the sum converges as you increase the partition, then it will be Riemann integrable. So that is the next thing to do. All right. So let me write the statement. Let f from AB to R is a well. It's an if and only if condition. So f is Riemann integrable if and only if there exists a real number A such that for every epsilon greater than 0 there exists a partition P which is, let's say, x0, x1, xn with summation f of tj xj minus 1 j from 1 to n minus is less than epsilon for any arbitrary points tj belongs to the subinterval xj minus 1 to xj, j from 1 to n. Right? And in the first year, you have seen that this a, this real number a, is the integration, right? Is this correct? Yeah. As this difference becomes smaller and smaller, whether this converges to some points, some real number, that will be the integration. That's what you have seen. Is it correct?
Yes, sir.
Okay. So now this was, so this part is our definition of integrability, uh, which means the lower integral is equal to upper integral, which means for some partition lower sum minus upper sum, or upper sum minus the lower sum is less than epsilon. So this part is that one, and this part is the definition you have seen in the first year. And this is the definition which Riemann also gave in his paper. I've uploaded the paper by Riemann in William, so you can see it. All right. Now remark is this A is nothing but integration fx dx A to B. So now let us first prove this way, which means assume f is Riemann integrable, and we want to prove this. Call this star to show star holds. All right. Now we'll use the fact that f is integrable if and only if there exists a partition for which the upper sum minus the lower sum is less than epsilon. So this is very important technique. So that one we'll use. Since since f is Riemann integrable, there exists a partition P which is x0, x1, xn such that what? Such that, well, this is for we need for every epsilon, such that the upper sum minus the lower sum is less than epsilon, right? Now, now what is the? Of course, we need to unfold the definition. So UPF is nothing but summation capital MI RMJ xj minus xj minus 1 j from 1 to n, and so and LPF is summation mj xj minus 1 j from 1 to n. Now you see that for Tj belongs to xj minus 1 xj, f of Tj will lie between mj to capital MJ, right? So this implies summation over j equal to 1 to n mj xj minus 1 less or equal to summation over j f of Tj xj minus 1, which is again less or equal to summation over j mj xj minus 1. All right. Now this one is lower sum and this one is the upper sum. Excuse me, just let me take this call. Yeah, sorry. Okay. So the point is this is one, and you see we also have LPF less or equal to integration a to b fx dx less or equal to UPF, right? This is true for every partition. This is true. Now, and we have, let me call this double star by 1 and 2, and this double star, we get that mode of integration, mode of summation j from 1 to n f of tj. We don't know which one is big, whether this one is big, whether this one is big, or this one is big, we don't know. Therefore, we just take the modulus minus integration a to b fx dx. This is less than UPF minus LPF, which is less than equal to, this is less than epsilon. All right. So therefore, we get star. The other side. So this part, what we need to do is to unfold the definition of lower and upper integral. So what to show, what to give, given is the following, given star to show f is Riemann integral. That is, there exists a partition P such that UPF minus LPF is less than epsilon. So that is for every epsilon greater than 0, there exists a partition P such that this. So this is what we saw. All right. So how to go with this? We want to show this, and we have star. So a star means this one. For every epsilon, there exists a partition such that this is true at tj or any arbitrary point in the interval. All right. So what to do next? Well, let's let mj is infimum of xj minus 1 to xj fx, and as we do, mj is supremum over xj minus 1 xj fx for j equal to 1 to n. All right. Now, since mj is infimum may not be attained. But what can you say? So what is the definition of infimum?
The element which is smaller than all the elements in the set. I mean, the
Elements will be,
largest element which is smaller than all the elements of the set.
that is true, but so if you have closed interval 0, 1, your
This is just
infimum will be -1, is it?
leftmost, leftmost.
The largest lower bound of a set is its infimum.
Yeah, largest lower bound. How do you make sense of it in terms of mathematics?
Sir, infimum is that element which satisfies two properties. First thing is any element of the set is greater than that. And the second thing
Yeah,
is there is no other element less than this element which satisfies this property.
yeah, that is true. That is true. But how close the elements from the set can go towards the infimum?
Arbitrarily close. It may also be equal.
Right, true. It will be, so it may be equal or may not be equal, but it will be a limit point, right?
Yes.
Yes, it will be a limit.
All right. So that's what we'll be using here. Similarly for supremum also, right? So to make here precise epsilon, we need to look at computation with epsilon by whatever 2 to the power n or something. Let me see what was it. Yeah, right. So instead of epsilon, we'll take epsilon by this one, epsilon by 2 to the power n into b minus a. So this is the thing we will go to make this one. So we don't need actually this one. All right. So there exists a point Sj or Tj in xj minus 1 to xj such that f of Tj minus mj is less or equal to or is strictly less than this. Right? So this is true. We'll get this one. You take any epsilon neighborhood of mj, you get a point from there. And also there exists a point Sj belongs to xj minus 1 to xj such that mj minus f of sj is less than epsilon by 2 power n b minus a. And the point is, this is true for every j 1 to n. All right. Now we get some number f of tj or f of sj closer to mj, capital mj, small mj and capital mj. So we now use star, this one. All right. So and you see here again, right. So you see here again this we also have this LPF is less or equal to summation j from 1 to n f of tj xj minus 1 less or equal to UPF. That is true in general for every partition. So we have this one also. And now we want to use this thing. Yeah, so let me see. So let us see how one can get towards this. Triangle inequality, of course. So you have, we now have UPF minus LPF, which is nothing but summation j from 1 to n capital MJ minus small mj xj minus xj minus 1. Now we incorporate these things, right? Summation j from 1 to n mj minus f of sj, right, plus f of tj minus mj xj minus xj minus 1, plus there will be another term. Let me write it separately. J equal to 1 to n, which is f of sj minus f of tj minus f of tj times xj minus xj minus 1. All right, this is the one. All right. Now, and there is, this is fine. Now you look at the modulus LPF, right, which will be less or equal to, we just divide each of the term, summation j from 1 to n mj minus f of sj xj minus xj minus 1. So these all are positive, so no problem. Plus summation j from 1 to n f of tj minus mj xj minus xj minus 1. Here also terms are positive, no problem. Plus summation j equal to 1 to n mod of f of sj minus f of tj xj minus xj minus 1. And here also f of sj will be bigger because it's near to capital Mj, and of tj bigger than f of tj, which is near to small mj. Right? Now what to do? Can we make this one small? So maybe I should put it just a bracket first and then modulus right here. This will be fine. So the first one, you see this one is less or equal to some epsilon by what? So we have epsilon by 2 to the power n b minus a. So summation 2 to the power n kind of. So j n from right. Yeah, this is very epsilon, very small. So one can do it epsilon by 2. There will be no problem, right? So it is n times n epsilon by 2 to the power n to b minus a will be there. And similarly here, you can put epsilon by 2 or smaller if you want. Here what we do is j from 1 to n, f of sj, xj minus xj minus 1 minus a plus summation j equal to 1 to n f of tj a minus f of tj a minus f of tj to xj minus xj minus 1. Is this correct? Yeah, I'm doing computations. So, I mean, of course, it is not that much motivating for you, but still, is this correct? So you just add and subtract by a with the whole thing, not just simple this, not just this one, but actually the whole thing, right? Now this one gives you, I mean, very small this quantity, right? So see this one, and there is n sum, and n sum, so you will have n times this, and which is of course less than this one. So what you get, this is less than epsilon for this partition. So this is less than epsilon. This is also less than epsilon. So what you get is less than epsilon by 2 plus epsilon by 2 plus epsilon plus epsilon. So it's a 3 epsilon. So this is fine, right? Yeah. So this is a positive quantity, therefore UPF minus LPF will be less than 3 epsilon. Since therefore, by previous theorem, right? By previous theorem, there is a theorem a few class back. F is Riemann integral. So is this fine with you? Anybody following this competition? Or followed this competition?
Yes, sir.
Okay. All right. So this is how we get whatever you've learned in first year is equivalent to whatever we learned the definition of integral, right? What next? Next is, so what next? So we'll ask the same question what Riemann asked. So what are all Riemann integrable functions? Functions, right? So question, does there exist a discontinuous Riemann integrable functions? Yeah, do you know an example?
Step functions.
Right, all step functions with the steps as steps as 1 steps as integer intervals. So step function, step functions, not necessarily integer. So whatever step functions are Riemann integrable. Now, then the question becomes: is are all discontinuous function Riemann integrable? Yeah. Do you know example of a discontinuous function which is not Riemann integrable?
One by x in -1 to 1 interval.
Yeah, it has infinite discontinuities. Right. So this is not even a, I mean, of course, discontinuous, let's say, we need boundedness. So now your example will not work. Right? It is
Sir,
unbounded.
sir, can we use that function for rationals? It takes 1, and for irrationals, it takes 0.
Right. So this is the function.
The Dirichlet
So
function.
right. So for rationals, these are 1, x belongs to q, intersection, let's say AB, and 0, x belongs to R minus q, intersection AB. So what is the upper sum? LPF of the interval of this function. Oh, sorry, lower sum
0.
0, and upper sum
B minus a. B minus a.
right. Upper sum will be b minus a. Right. So if you choose b is strictly greater than a, so you see that this is quite far for every partition. This is true for all partition, right? Therefore, f is not Riemann integrable. All right. So therefore, question becomes: so this is a valid question. So this is a valid question. What are all Riemann integrable functions, right? So it must be with something to do with the discontinuities, right? Because all continuous functions are Riemann integrable, continuous in a closed interval. So it has to do with some discontinuities. What can be the set of discontinuities so that it will be Riemann integrable? So first question is a simpler question. Suppose you consider a function which has only one discontinuity. Is it Riemann integrable?
Yes, sir.
Yes.
Yes, sir.
Yeah. How do you think?
If we have only one discontinuity, then
Yeah.
the change in the sum, suppose we are calculating the upper sum and the lower sum, the
Right.
change in the sum will occur in either in a maximum of two partition. Either it will affect the sum over two partitions or one partition, or it will not affect the sum at all. But even if it affects these two partitions, taking the partitions arbitrarily close will, I mean, erase that difficulty. So it will converge.
Right. So your argument is going to the right direction. So let me give you the what is the idea. So the question is, suppose A from AB to R has only one discontinuity. Is it Riemann integrable? Its answer, as you said, few of you, Answer is yes. It is. The point is like here. So look at this picture.
Sir,
Yes.
here should not be a condition applied that it should be bounded also, because 1 by x has only one discontinuity at x equals to 0, but
Right,
still
right,
it
right.
is not Riemann integrable.
Right. Right. This is good. Thanks. So if suppose a bounded function, so boundedness is important. Suppose a bounded function f. So boundedness is this is very important. So for unbounded function, Riemann integral generally doesn't exist. So those things are called improper integral, which we'll see later, most probably. Yeah. So look at this one. Look, suppose you have a discontinuity. So bounded function, it has at most jump discontinuity. So something like this. Now the point is here. Here there is a problem. Right? So this should come near to this one, but not exactly. So there is a problem here. Let's call this as, let's see, C, x equal to C. This one. Now the point is, so suppose this is A and this is B. So you clearly see that finding area is not a troublesome here. Once we know this, these two parts are integrable, right? So one would consider the area of this part. One would consider area of this part. But if you look at lower sum and upper sum stuff, so let me look at a division. Look at a partition. Right. So this is x0, and this is x1. So the problem part is this one, right? Problem part is this one. This part. Here you see the here you see the infimum and supremum has huge difference, right? That can be huge. So you cannot bound this the functional value supremum minus infimum. That one cannot become small at the point of singularity, right? Is this clear? So in that interval containing the point of discontinuity, the supremum minus infimum, that cannot become small, right? So when he proved that the continuous function is integrable, what we used crucially is as you look at smaller and smaller partition, your supremum and infimum becomes less than epsilon, right? Whatever is small epsilon you like, right? Because of this uniform continuity stuff, right? So what we really needed is the following. We need to make the following sum small. small, right? Summation mj minus mj xj minus xj minus 1, right? This is nothing but UPF minus LPF. All right. So we need to make this sum small, which means as you go to the partition, what you need to do is you look at the partitions. Right. So here in the interval where subintervals rather, where f is continuous, we will make this part small. This is possible. And near the point of discontinuity, this part is not always small. So to make the sum small near the point of discontinuity, we need to look at this one. So near the point of discontinuity, we make the length of the subinterval small. That is possible, right? So you look at a partition, but here instead of giving big partition here, you fix a partition here, very small, so that the area you get for this one will become very small. Though the supremum minus infimum is big, but the area, this one, becomes small. So this make this area small. All right, do you get the idea? This is the idea behind the next few theorems to come. Wherever there is a discontinuity, you will make the area small, making the subinterval, length of the subinterval. So you make a refinement here in this small portion so that this area becomes very small. Right? Let it be other part. There is no problem. But this one, especially this one, yeah, any question?
Yeah, so one thing I was wondering, sir. So we basically want to find for a given epsilon one partition which will make the entire sum
Right.
small.
True.
So,
Yes.
I was thinking, why don't we, if we choose a partition which has the point of discontinuity on the sequence, then this problem of capital M minus small m being rather large, it won't turn up in the first place, right?
Well, it may. Well, that is. No, here you see here the functional value will be this one, if you closed interval, so you are looking at closed interval, right? So there is a difference. So here you look at the point C, and suppose you have this interval x, j, comma c, right? This is what you mean. So at C value is this one. So you have the difference big. Do you get my point?
Oh, okay, got it.
Yeah. So there will be difference if you take this as endpoint. So precisely we should not make it an endpoint. So we'll choose partition in such a way that this should not lie at the endpoint. It will be in the interior. All right. And that's where this length you can make small as you want, so that the area also will become very small as you want. All right. So you'll look at the sum of this sum into two separate parts, one near the discontinuity, others in the other part. So for continuity, as we did for continuity, we'll go with that. And near the point of discontinuity, we'll divide the interval further to make this length xj, xj minus 1, xj minus xj minus 1 very small, so that the area would be less than epsilon by 2 to the power n or something. Epsilon by 2, 4 or epsilon by 8, whatever we need. All right. So this is the idea behind the proof of the fact that has one discontinuity implies Riemann integrable. That would give you finitely many discontinuity implies Riemann integrable. So the full proof is written in the notes. Okay.
What happens if C is one of the endpoints of the interval?
So if C is one of the endpoints, then you have, suppose xj is this one and C is this one. So let me take a different color. So xj is this one and C is here. Here is C. Now you see here, the infimum will be lying here, right? Somewhere here. And supremum will be lying here. Right? The difference is big. So this one is big. And this one you did not make small.
I'm sorry, I meant if C is one of A or B, because in that case you cannot get around this.
If A and B, well, then there is no problem. You will just put it like that. I mean, you will. So if x equal to C is here, you make this one very small. There will be no problem here, whatever the thing is there, because there is no other side, right?
Yes.
So if this is this one, whatever, you can make this length small. Here there is no choice. At the endpoint you have to be endpoint, right? But in the interior you can make this small, this part small. So here we'll separate this part. So this part, sorry. Okay. So here keep on making it small. So this one would be as small as possible. Right. So you'll take this one very small, so that so that this area will become small. Right. If it is A and B, the same. This would be the problem. So that is why you can actually remove one point endpoints, right? Whether you are integrating on open interval or closed interval doesn't matter, right? So this is the same procedure will go here. Of course, one can make it endpoints, but then it will affect two intervals. You have to work with two separate same kind of calculation, but in the middle you have to do once only. That's the reason you are looking at the point of discontinuity in the middle, not as the endpoint. Here it will be affecting only one interval. Here also it will be
Sir.
effectively bounded. Yes.
Sir, is it okay to say that the intuitive reason behind one discontinuity or countably many discontinuity not affecting the integral is because that the rectangle of any one interval is zero when we take when we go on refining, it tends to zero when we go on refining. So any one rectangle having a difference in the infimum and supremum doesn't really matter.
Right, because you can make this interval very small. Yeah, but if you have
Go on refining.
countably many discontinuities, it will have limit point. Then you have to work with that limit point.
If it has
Right?
What
If
is-
you have countable infinite discontinuities, then you will have limit points.
no, I said if you have countably many discontinuities, then I mean no countably finite.
Yeah, then
Or
it will be
one.
the same way.
It's the same
way.
thing because one rectangle, the area of one rectangle doesn't really matter.
Right. One small, as soon as you are making the length, the width small. Right. Those finitely many points, you can do that same procedure, and remaining part as in continuity. So you'll get with finitely many points. Well, even then, infinitely many discontinuities can also be tackled. So there you need to consider the limit points. Okay. So this in the notes there will be one proof of 1 points, and then for finitely many points. So please look at the detailed proof of these two things. And we'll start with when there is a limit point for the point of discontinuities. Okay. Tomorrow.
So what about the other types of discontinuities? So like this intuition here, it is working for a jump, but what about something like sine 1 by x? That is also Riemann integral.
Yeah, sine 1 over x. Yeah, so what is sine over is? Yeah, so as soon as the function is bounded, you can define this way. Right? As soon as function is bounded, you can define this way. There will be no problem. So the only thing we are leaving here, leaving from here, is the infinite discontinuities. Okay, so sine 1 by x is 0 is the only singularity, and you can do the same procedure with 0. So this will be very this will not be small, it will be less or equal to 2, but this will be very small, right? So that part near 0 it will be very small. Other part as in continuity. So as soon as function is bounded, you can define this way and see whether this limit exists or not. Yeah, does that answer your question?
So it works because mj minus capital MJ minus small mj is bounded. So we can take arbitrarily more refined. We can refine xj minus 1.
Right. True.
So that it works.
Yeah, that's the idea. Whenever this part, you cannot make this small, you refine this interval so that this becomes very small. As soon as you can do it, you have no problem. But of course, this cannot go to infinity. Hence, we assume the function is bounded. All right. Any other question? Yeah. Okay. So let us. So we'll meet you tomorrow. All right.